The Chebyshev algorithm utilized in the paper has a basis found within the Diffie-Hellman passkey scheme. So in order to actually understand first how the Chebyshev algorithm properly functions, the Diffie-Hellman algorithm had to be first examined. As we can see here, I created a program that computed a Diffie-Hellman passkey for two users within the simulation. So when we run the program, it has its first known numbers of G and P, which are the prime numbers which are required to then compute its personalized key, which is then sent to the destination host. From there, the second host creates its own key and then sends its secret key to the first host, Alice. And then from those two numbers that are then sent to each other, using a modular and the exponent, you can then compute a Diffie-Hellman algorithm in which you have the same value for both hosts. So we'll see here, when we run the program, we see that Alice creates the generated secret key of 7. Bob creates a secret generated key of 5. And then when they both transmit each other's passkey to one another, it then creates the same exact passkey, therefore allowing successful key generation between hosts and then establishing a successful connection. We can also look at this in a more complicated version in which using hexadecimals, which is more likely to be used within a network situation. So in the second Diffie-Hellman, we'll see here that we have our key, initial key here within this array. And when we run it, it does take a little more processing time, thus why I didn't use it within the microcontroller. But once again, we find that the original key and then the key made for Bob generation, once shared, both equal the same exact thing. So then when we go over to the Chebyshev algorithm has a similar principle in which each creates its own particular key, and then when shared and then modified with their original key with the received key, it then produces a same shared key between both hosts. However, the process is different. Within this one, I use a nested statement to then create it, so it has an iterative function within it to actually calculate the Chebyshev algorithm faster. So with this, it actually created a more complicated value within its actual development, therefore making it actually a more complicated and more difficult algorithm to actually decrypt, just because the actual values are larger and require slightly more processing power to actually compute it. And so once again here, we'll run it and we'll see that once again, Alice computed the 7th iteration of the Chebyshev algorithm for its x value of 3, and it came out to a value of 3. And Bob had computed the 5th algorithm of the Chebyshev with the same value of 3 and created 14. However, when they were moduloed between each other within the equation, when they both share each other's numbers, we found that both Alice and Bob then came to the value of 42 in creating its own specialized passkey. Now, all this is done on a network through Zigbee micro modules. And the Zigbees actually are a very handy device to use within the code and the presentation of this device because of the fact that they are low power, which is one of the fundamental things required of this project. And additionally, they actually can handle the encryption. Now, we didn't actually use the encryption implicit within the Zigbee module. We actually did that within the mplab code. And we'll see here where we actually send it with its key in AES here and then sent it out rather than using the Zigbee, because this gave us more control over the actual display and implementation of the code. Whereas if we had it running under the Zigbee, it would always be encrypted if we enabled it, and it'll be a little more difficult to actually demonstrate within the video. So utilizing the Zigbees, we actually created a very secure platform utilizing low power schemes and low processing power, which will be required for these small scale devices, which will be used on these body sensor networks to detect the heart rate, the temperature, the humidity, and any other variables that the doctor or device will require of it.